Alright guys, welcome back. We'll look at 6.4, which is sketching trig functions. So basically it's about transformations of the trig functions that we're used to. So it says, transformations again. At this point, we should be relatively familiar with transformations. We've spent a lot of time with transformations over the last couple of years. The big difference in this section is that we're going to focus mainly with radians as opposed to degrees for the graphs of sine and cos. So we know about these transformations that we have here already. If we have negative out front, it's reflected over the x-axis. If we have the negative in with x, that's reflected over the y-axis. If we have an a value out front of our function, that's vertically stretched or compressed. If we have a k value in with our function, with our x values, that's going to be horizontally stretching or compressing it. The base form of our equations will look like these over here on the right. Same spots as you would expect them. The only difference is you might have the word sine or cos in here. But basically looks the same. Before we just had f. So if it's trig function, you see sine or cos. Same mapping diagram that we saw before to figure out what happens to our points of the base points of sine or cos based on our transformation of ak dc. Now let's go through our base points. These are the same ones that you used last year. What we're going to try to focus on would be these over here. These are the radians, right? 0 degrees is 0 radians, 90 degrees is pi over 2 radians, 180 degrees is pi radians, 270 degrees is 3 pi over 2 radians, and 360 degrees is 2 pi radians. You should know those already, I hope. If not, maybe that's something that you study. But let's go through what our base points were. If you remember what the sine graph looked like, basically it started at the origin at 0. At 90 degrees, it was up at 1. Then it was back down at its x-intercept. 270, it was down at its minimum of -1. And 360, it was back at its x-intercept. And we continue on. Our cos graph, a little bit different. Cos graph just starts at its maximum, 1. Goes down to the x-axis. Goes down to its minimum. Back to the x-axis, and then ends at its maximum 1. So really the idea is the x values stay the same for sine and cos. The only difference is the starting point of the two graphs. So let's go through some characteristics that we should be familiar with. Characteristics of sine functions. The amplitude. Now what the amplitude is, it's always a positive number because it's a distance, and it's the distance that would be created. I'll draw a graph over here actually. Maybe a sine graph. The amplitude is the distance between the middle of the graph. We're going to call that the equation of the axis in a second. And its maximum or minimum. It's always a distance, so we refer to it as a positive number. The period is how long it takes for one cycle to complete, because this graph continues on. But one cycle would be where it starts and returns to that same spot to continue the same cycle again. So that would be one period. So one cycle is completed over the length of one period, of a period, not one period, 360 degrees. Is the base, or 2 pi. The axis of the curve, or equation of the axis, is a line that is halfway between the maximum and minimum that our graph oscillates around. When I say oscillates, it means it goes up, and it goes down, and it goes up, kind of like a swing. And a phase shift is how our graph is shifted to the right or to the left, basically horizontal translations. So let's have a look at our graph. So in these ones, we're going to be working with radians. So state the amplitude, the period, the equation of the axis, and the period, and the phase shift. Let's use this color. One thing that I didn't really touch on, but I guess I should, is the period. It's equal to 2 pi over k. The amplitude is the a value in our transformation. The c value is the axis of the curve, and the d value is that phase shift. So A, D, and C are important. K is not the period, it's 2 pi over K. So let's go through those. So amplitude. Well, that's our A value. It's the absolute value of that A value, so it's 2 in this case. It's already positive. The period. Well, that's 2 pi over K. In this case, K is 3. So our period is 2 pi over 3. And that makes sense because a K value of 3 means that our original graph, so let's suppose this was the graph, it has been compressed together. These points are pushed together. So, you know, this point now begins here. This point is moved in, maybe now it's here. And you can see that that cycle is completed in less than the original. So 2 pi over 3 is less than 2 pi. So it's been compressed in that case. K value of 3 compressed. Keep going. Next one was axis of the curve. They also call it equation of the axis in some books. That's our C value. In this case, it is positive 1. That means that equation of the axis has been shifted up or down. And in this case, no phase shift. We'll use brown for that one. Because d is equal to 0, there's no d value. Let's try next one. Amplitude, that's the value that's out front. Remember, it's the absolute value of A. In this case, positive 3, right? It's a distance. The period is equal to, in this case, my K value is, maybe I'll zoom in here a bit, is, well, coefficient on that is 1, so 1 over 2. K value has been distributed inside here, and we'll look at that in a second. So period was 2 pi over K, which is 2 pi over 1 over 2, which is 4 pi. Our equation of the axis, or axis of the curve, is the C value, and that's 4 in this case. Right, the value that's at the very end, same as we've always seen. Now our phase shift. That's our D value. Now in this case, our K has been distributed inside. Because remember, it was like this. K is equal to theta minus D. If I distributed K inside, that D value would have a factor of K. So I'm going to have to factor that out because I need to have theta by itself. So if I'm factoring it out, I might if I factor out half theta minus, and I figure out, well, how do I figure out what that value should be there? Well, the idea is when we're factoring, we're dividing. So I'm dividing this by a half. When you divide a fraction, it's the same thing as multiplying by its reciprocal, which is 2 pi over 3. So then you can say, does that make sense? 2 pi over 3. Well, you can think, well, that's if I distribute back inside. Do I get the original one here? So half times theta is theta over 2. And you say, okay, well, how about half times here? Well, that will make the bottom 6. 2 divided by 6 is 3. So you will get pi over 3. So you can test it. So in this case, now I see negative, or subtract 2 pi over 3. Well, that means it's phase shift to the right, 2 pi over 3. And there we go. Keep going along here. Now these ones want us to sketch what we've got. So we're going to state our characteristics. So just like before, our amplitude is the value that's in front. Whoops. In this case, 4. Our period is 2 pi over K, so it's just going to stay as 2 pi. Because K is 1. Right? There is no value. It's like 1x here. Our phase shift, there's no D values, so no phase shift. And equation of the axis. In this case, there's no C value, so it's like plus 0 on the end. Right? Like plus 0. So equation of the axis is at 0. So how do we graph these things? Well, first thing you're going to look at is what graph we're looking at, the coast graph. So I'm going to list all the points for the coast graph. So I'm going to use red. We have x and y. We know the coast graph already. We already wrote it above. 0 and 1. Pi over 2 and 0. Pi and negative 1. 3 pi over 2 and 0. And 2 pi and 1. Like I said, coast graph starts at the top, goes down to its minimum, back up, and at its maximum. So you don't really have to memorize as long as you know what the graph looks like. So let's transform this based on our, well, I guess it's only an a value in this case. You might remember that it's x over k plus d ay plus c, but in this case there is no k, d, or c. It's just an a value of 4. So x's will be staying the same. Our y values will be multiplying by 4. So I'll write on the x values still remaining the same. My y values multiplying by 4. And we can plot this onto our grid. Now for your scale, what you can usually do is find the largest denominator, in this case 2, and have each square go by one of those. So since it's 2, it'll go 1 of 2, or half. So I'm going to make these go pi over 2. 2 pi over 2 is just pi. 3 pi over 2. 4 pi over 2 is just 2 pi. And I can continue that way, 5 pi over 2. And so on. So that's one kind of trick to make things a little bit easier. So let's graph those points. So use purple. So 0 and 4. We're going to have half and 0. Pi and negative 4. 3 pi over 2 and 2. Back up at the top. And that's our graph. If I was wondering what the original graph looked like, well, it would have been something like this. You can see that the purple one is a lot more stretched than the base graph for coast, the red one. If I wanted to look at the characteristics of it, well, the equation of the axis is the line that splits it in half. So we said it was at 0. That's kind of a line that goes through here, I guess. The amplitude is the distance from bottom to top. So from here to here works out to be 4. Same from here to here works out to be 4. Same here to here works out to be 4. So the amplitude is 4 in this case. There is no phase shift. The way that I can tell is because our graph starts at its maximum where the coast graph is supposed to begin. Right? If the first dot was like over here, for example, there must have been a phase shift to the right. And the period, how long did it take? Well, it started at 0, ended at 2 pi. So the difference between those ones, 2 pi take away 0 is 2 pi. That's the distance from here to here. And that's that first graph. So let's continue along. We'll look at the next one. Next one's a sine graph, so we're going to have to use the base points for that. But we'll go through all of our characteristics. Our amplitude, that's the a value that's out front, in this case 2. My period, that's 2 pi over k. In this case, k is 3. 2 pi over 3. No phase shift happening here because we don't have a d value. And our c value, our equation of the axis, is 1. Okay, this was our c, that was d. This one incorporated k, was on the bottom, and a. So let's go through our base points. I know that we're working with sine. That word's important because I'm going to use the x and y points for sine. Sine starts at the origin. Then at 90 goes up to its maximum, right? So it starts here, goes up to its maximum, comes back down, goes down to its minimum at -1, 3 pi over 2, -1, and ends at 2 pi at its x-axis. So I want to transform our base points. So just like before, it was x over k plus d. All of that was ay plus c. So my k value is 2 pi over 3. Or no, that's my period. My k value is 3, so it's x divided by 3. My d value, we don't have one, so all my x values are being divided by 3. My a value is 2 and my c value is 1, so 2y plus 1. And let's go through these. Oops, sorry, what happened there? All right, we're back. All right, so x divided by 3, 0 divided by 3, 0. Half divided by 3, so how do I do that? Half divided by 3. Really what happens in that case, if you imagine, half divided by 3 is the same thing as multiplying by its reciprocal. It becomes pi over 6. Really what happens is the denominator just gets multiplied by that. So it was 2, now it's 6, so that 3 basically multiplied the denominator. I'm going to do that, so we get pi over 6. Next one we have pi divided by 3, which is just pi over 3. Next we have 3 pi over 2 divided by 3. Well, that's 3 pi over 6, which I can just make pi over 2 if I reduce it. And the last one, 2 pi divided by 3 is just 2 pi over 3. Y values multiply by 2 and add 1. Like so. And let's plot these onto our grid. So what I'm going to do is I'm going to look at our graph and I'm going to see what are our smallest denomination that we have. Now in this case I see pi over 6. So I'm going to use pi over 6 as my. So pi over 6. 2 pi over 6 is pi over 3. 3 pi over 6 is pi over 2. 4 pi over 6 is 2 pi over 3. 5 pi over 6. 6 pi over 6 is just pi. 7 pi over 6. 8 pi over 6 is 4 pi over 3, right? We're just reducing them. And let's plot these points onto our grid. So 0 and 1 will be right here. Pi over 6 and 3. Pi over 3 and 1. And there we go. That's our graph for 2 sine 3x plus 1. The original graph, if we remember what it looks like, it would have been started here, and it would be up at its maximum here, minimum, and continue on. Where would it be? Down here and then back up. So it's kind of running off the grid for this one because of the scale I chose. But you get the idea of where that graph, so it's been compressed in this case. Right, that's a k value of 3, compressed this graph. We can look at the equation of the axis of this graph too. Equation of the axis for sine graph just passes right through here. It oscillates up and down. Amplitude, in this case 2 from here, and it goes down to from 1 down to -1. No phase shift happening there, so that's that graph. All right, so let's continue along for the last one here. So sketch one cycle of this graph, state the amplitude. So amplitude is number out front, so amplitude in this case, 3. Period. Well, remember the period is 2 pi over k, which is a half, which is 4 pi. Dividing by half makes the same thing as multiplying by 2. Phase shift. So I have to look at what we've got here. And I notice that k has been distributed inside, so I need to take out half. So I have to take pi over 12 and divide it by a half. Same thing as dividing by half is multiplying by 2 to give me pi over 6. So I have a phase shift right, pi over 6. And as we continue along, last one we have is equation of the axis. Equation of the axis in this case is the value that's at the end, in this case 0, because there is no c value. Now let's come up with our base points. Our base points are based on what word we're talking about. In this case, we're just coast graph, so I'm going to be using the coast points. 0, pi over 2, pi, 3 pi over 2, and 2 pi. For the y values, we know that the coast graph starts at its maximum at 1, goes down to the y-axis, down to its minimum at -1, back up, and to the maximum 1. We want to transform our graph based on AKDC. So x over k plus d, right, use that mapping. We have ay plus c. And let's figure out what's going on here. So the k value is a half. So we have x divided by a half. Now remember, dividing by a half is the same thing as multiplying by 2. So I'm going to have 2x. Right, you might say why? Well, x divided by a half could be written like this. Is the same thing as multiplying by its reciprocal, which is 2x. D value in this case, we found out it was pi over 6. So I'll put that in. A value is -3 and C is 0. So multiply my y values by -3. So first one, 2x, so it's basically saying 2 times 0 plus pi over 6. That's pi over 6. Easy one for the first one. Next one we have 2 times pi over 2 plus pi over 6. So I'll do a little bit of work here. We're going to get pi plus pi over 6. Well, if I'm getting common denominators, add them together, 7 pi over 6. Next one, we have 2 times pi plus pi over 6. Multiply them, 2 pi plus pi over 6. Get common denominators. For 2 pi would be 12 pi over 6. Add them for 13 pi over 6. And you probably see a pattern happening here, and usually you might see all the numerators are increasing by 6. So I know the next one's going to be 19 pi over 6, 25 pi over 6. I could solve them through too, right? So let's take, I don't know, the last one, 2 pi. 2 times 2 pi plus pi over 6. Get 4 pi plus pi over 6. Common denominator, if I need 6 on the bottom, I need to multiply the top and bottom by 6. So 4 times 6, 24. Add them for 25 over 6. All my y values need to be multiplied by -3. So we're going to get like so. And we're going to sketch these ones. Now this one here, the graph's a little bit small, but we'll see. So I look for the smallest denomination. In this case, I see pi over 6. 6 is the denominator for them all, so I'm going to make each a factor of 6. Now in this case, it's going to 25 pi over 6, so you're going to see that it's going to be off the graph actually. So maybe what I'll do is I'll add a few more in here because the scale for this graph's not the greatest. But we'll do pi over 6. 2 pi over 6 pi over 3. 3 pi over 6 is pi over 2. 4 pi over 6, 2 pi over 3. 5 pi over 6, 6 pi over 6 is pi. 7 pi over 6. I'll do every second one here. 8 pi over 6. 4 pi over 3. 8, 9, 10 pi over 6. Can reduce it. 11 pi, 12 pi over 6. 13, 14 pi over 6. You can reduce each of these ones. Oh, that should be 16. 18 pi over 6. 20 pi over 6. So we go up to 25. So it's going to be a little bit off the graph there. I should have made a little bit longer graph here. But let's go through these. Pi over 6 and negative 3. Down here. 7 pi over 6 and 0. Right there. 13 pi over 6 and 3. And 3 would be right there. 19 pi over 6 be right here. And 25 pi over 6 will be, 21, 22, 23, 24, 25 pi over 6, somewhere down here. I know it's off the graph, but hopefully you get the idea. So with this graph, it's because the period's so long why it's off the grid, but the idea is we have equation of the axis. In this case, we said it was at 0 right along this line here. The amplitude is the distance to the top, which is 3, or the distance to the bottom, which is also 3, right? It goes down to negative 3 and up to positive 3. Phase shift, pi over 6. So if you see the graph does not start on the x-axis, it's actually been shifted to the right, pi over 6, as we can see. That's all the characteristics, I think. Oh, the period. So if I need to find out the period, it's between pi over 6 and it ends at 25 pi over 6. So what's the difference between those? Take away pi over 6, which is 24 pi over 6. When I divide that, we get 4 pi. So that's one period. You can subtract the end from where it began. And that's that one. If you have any questions, let me know. There's a few questions down at the bottom that you can try for the sketching of these for the transformations.